So today's speaker is Dr. Nicolas Delfosse. Nicolas obtained his PhD in mathematics from the Université de Bordeaux in 2012. His thesis was entitled Construction and Performance of Quantum LDPC Codes. Between 2012 and 2017, he held various fellowships and postdoc positions at École Polytechnique, Université de Sherbrooke, and Caltech. In 2017, Nicolas joined Microsoft Quantum in Redmond, USA. He now works as a senior researcher specializing in the design of quantum error correction. And we're extremely happy to have you on the call today, Nicolas. Thank you for waking up at this ungodly hour over on the other side of the Atlantic. And with this, the virtual floor is yours.
Thank you very much. Thank you for inviting me. And I'm going to talk about this recent work that we did with Maxime Tremblay and with Michael Beverland. And it's about one of my favorite topics. It's about quantum LDPC codes. And the reason why a lot of people are excited about quantum LDPC code is that they could offer quantum error correction scheme and let us build fault-tolerant quantum computer with fewer qubits than surface codes. So in theory, they could outperform surface codes, which is the most popular scheme today. But there is still a gap between theory and practice. And here, it's what we are trying to close. We're trying to close this gap and make them more practical and trying to see if we still preserve this improvement of quantum LDPC codes. And by implementation, I don't mean that we built it. It's a family of codes that works with many physical qubits. We need thousands of qubits. It's long-term research, but I mean that we propose a scheme to implement these codes. And the main issue is easy to see if we look at the typical structure of those LDPC codes. Those LDPC codes look like a random graph. It's a sparse graph, and they look highly connected, unlike a quantum computer. A quantum computer, if we think about superconducting qubits, it's a square grid of qubits with local gates. So the problem is, how do we map this quantum LDPC code onto our quantum hardware? How do we implement these codes with local gates on a quantum computer? And I'm gonna try to add a pointer. Okay. And our main result, the take-home message, is that with 2D local gates, it seems challenging. We first obtained a lower bound on the cost of these codes, a lower bound on the depth, and a lower bound on the number of ancilla qubits needed. And we designed circuits that reach this lower bound that are optimal up to a constant. And with these circuits, our simulation show a poor performance. So it's the pessimistic answer. And to avoid this issue, we design a scheme based on not only 2D local gates, but 2D qubits on a 2D plane with long-range connection, but only a few layers of planar long-range connections. And with this additional type of operation, we obtain a good performance, and we show that numerically they can outperform surface codes.
Okay, so Nicolas, I have a question from someone in the audience. They ask, could you define layers in this setup?
Yeah, I'm gonna get back to that. My goal is to convince you about these 4 points, and I'm gonna talk about the layers at the end of this talk.
Thanks.
But thank you. Please ask again your question at the end if it's not clear. So first, I'm going to talk about surface code and see how what LDPC code could offer. So I'm going to review surface code quickly. So the goal of quantum error correction is to go from current qubits or near-term qubits that have a noise rate of 1% to to 10 to the minus 4, let's say. And to run quantum algorithm, to run large-scale quantum algorithm with industrial applications, we will need qubit quality with noise rate close to 10 to the minus 12 to 10 to the minus 15, depending on your application. To go from current noise rate to the required noise rate, we need error correction. Error correction will let us increase the quality of our qubits. And the most popular scheme is the surface code. So the surface code, it's a square grid of qubits. Here you can see a grid of 5 by 5 qubits. And you have local measurements that you implement on the square plaquettes or on the boundary plaquettes. There's two types of measurements. And when an error occurs in the surface code, it is detected by the outcome of the plaquettes. The outcome of the plaquettes is +1 when there is no error. And if there is an error, the neighborhood of the error will detect a -1 outcome. Will give us a -1 outcome. So we can detect and correct errors with these plaquette measurements. And in practice, how do we implement these plaquettes measurements? We need to implement a quantum circuit to extract this information in the center of each plaquette. And this quantum circuit looks like that. This is a circuit we do on one of the two plaquettes, and the other one is similar. So we are going to prepare an ancilla qubit in the middle of the plaquette, and then we're going to apply 4 gates, 4 entangling gates that will connect the middle ancilla with the 4 qubits of the plaquette. So we do 4 CNOT, and then we measure this ancilla qubit. If there is an error on one of the 4 qubits of the plaquette, it's going to flip the outcome. So instead of an outcome +1, we are going to observe an outcome -1 and detect the error. And in practice, we can extract the syndrome of all the plaquettes, extract the measurement outcome of all the plaquettes simultaneously. It's one of the advantages of surface code is that in 6 steps, we are going to extract all the measurement outcomes. So this is a 3 by 3 surface code. And the circuit looks like that. First, we prepare an ancilla qubit in the middle of each plaquette. Then we implement in 4 rounds the 4 gates connecting this ancilla to all the qubits of the plaquette, to the 4 qubits of the plaquette. So it's either Z, control Z, or control X, control NOT, that we use depending on the plaquette. And we can implement these 4 gates in a specific order, and we measure our ancilla qubits. So we can implement the whole syndrome extraction circuit in 6 steps. It's a fast syndrome extraction. And why do we like surface codes? We like surface code because they have a high threshold. That means if all your gates and all your operation on your qubits have a noise rate below 1%, you know that you can just increase the system size, increase the lattice size, and it's going to give you a better logical error rate. So you can achieve any logical error rate by starting with qubits with a good enough quality, and this threshold quality is very high. It's 1%. And the second thing we like is that it's 2D local. As you can see, we can implement the whole syndrome extraction circuit. We can run error correction with only local gates. So it's well adapted to current hardware. And the main issue is that it's very expensive. We need thousands of physical qubits per logical qubit. This one, for instance, is a code that can be used to run Shor algorithm. And you need a 25 by 25 lattice of qubits to encode a single logical qubit. So you need 1200 physical qubit per logical qubits. And this is why we would like to use LDPC code, to use much fewer physical qubits per logical qubit.
So I have another question here, Nicolas. Someone is asking, the physical error rate, is that the error of the operations, or does it include errors on initialization of qubits as well?
Yeah, so it includes everything. So what we do is, to simplify, we assume that all the operations we can do on our physical qubits have the same noise rate. Let's say we take the worst of all the operations. And by all the operations, I mean, we select a set of operations. It's going to be preparation of a qubit in the plus state, for instance, applying Clifford operation or a T-gate, and applying a CNOT. This is enough to have a universal quantum computer. And now I will assume that all of them have a noise rate 10 to the minus 3. If all of them have a noise rate 10 to the minus 3, and I encode my physical qubit to build logical qubit with a 25 by 25 lattice, I get a logical qubit with noise rate 10 to the minus 12. Okay, now, why do we care about LDPC codes, about quantum LDPC codes? So I'm going to briefly review some of the papers that motivate LDPC codes in the quantum setting. The first one is in 2004. It's McKay, Mitchison, and McFadden. And they propose to generalize LDPC codes, which are very popular in the classical setting, to the quantum setting. In the classical setting, these codes are everywhere for classical communication. They are in your cell phone with 4G or 5G mobile. They are in your Wi-Fi. They are in the flash memory, the main memory of your laptop. And they generalize that to the quantum setting. The main issue is that the generalization seems to perform well, but has a poor distance. So the error correction capability is limited. It's a log distance in this paper. And a few years after, there is a first satisfying construction of quantum LDPC code, which moved from a log distance to a square root of n distance. So we can correct a larger number of errors with this family of LDPC code. And this is Tillich-Seymour code. It's hypergraph product codes. It's a code we are going to simulate. And to move from the existence of those codes and classical and communication to quantum computing, there is this paper of Gottesman that shows that we can reduce the cost to a constant factor. The cost of fault-tolerant quantum computing can be a constant factor. And this is done by encoding not with the surface code or with other topological codes, but with quantum LDPC codes. We encode many logical qubits together to form a large block, and that allows us to reduce the cost of fault-tolerant quantum computing. The issue is that at this time, there is no code that satisfies all the assumptions in this paper. So Gottesman identified a family of codes of quantum LDPC code that will give us constant overhead. And later, it was proven that the family of Tillich and Seymour, the hypergraph product code, do contain codes that satisfy all the assumptions of Gottesman. And then to move from a theoretical asymptotic result to a practical result, we need to do some simulation. And there was some simulation with a simplified noise model, phenomenological noise, that shows that they have a high threshold. So it's very encouraging. And another very exciting result is that quantum LDPC codes with good minimum distance and good encoding rate exist. We didn't know that until a few months ago, and it's a great result by Penteleyev and Kalachev, and it's going to even further improve the performance of quantum LDPC code. And it was an open question for a few decades. It's a very strong result. Okay, so now I haven't told you what LDPC code means. I'm going to give you a graphical definition of classical codes and quantum codes. The reason why I like this graphical definition is because it's the same for both families. It's almost the same. So a classical codes, here I mean classical linear code, and they encode a bit string where each node here corresponds to a bit. So we have a bit string with length 7, which encode data by satisfying parity constraints. So each square in the bottom, it's called a check, is a parity constraint. That means that the parity of the 4 connected bits must be 0. And we have 3 parity constraints. So we have 7 bits, 3 parity constraints. There is 4 logical bits remaining. And if there is an error, if we have a bit string that satisfies all the parity constraints, and we flip one of the bits, it's going to change the constraint that is incident to this bit. So it's going to give us a constraint that is unsatisfied, a check that is unsatisfied here. And it tells us that there was an error, there was a bit flip, and we can use this information to correct the bit flip. This is how classical error correction works. In the quantum setting, it's almost the same thing, but on qubits, we have 2 types of errors, X and Z Pauli errors, or both of them simultaneously, which give us a Y. And we use 2 codes, 2 classical codes to correct these 2 types of errors. We use one code in the bottom, one set of checks in the bottom that correct X errors, and one set of checks on top that correct Z errors. And this is enough with these 2 types of checks, which correspond to, in the surface code, to the 2 types of plackets. It's exactly the same formalism. We can define a quantum code, and we'll consider codes from this family. It's a family of CSS codes. And by LDPC means low density parity check. So it means low density sparse, because these codes are defined by low degree graph. This is what the family of LDPC code is. It's a family of low degree graphs. Okay, now I'm gonna first consider the case of 2D local gates, and then we're gonna consider what we can do with long-range connection. So I'm going into the first part, the first set of our results, which is the pessimistic answer. It's not going to work in 2D with local gates, basically. And what kind of circuit do we consider? We consider circuits that are made with 5 types of operations. First, we can prepare a qubit in the state 0 or plus. So we see a preparation here. Then each qubit will correspond to a horizontal line, a dark horizontal line. It's a qubit, and the blue lines are classical memory. We will need to represent the classical memory to be more accurate. And we can do single or 2 qubit Pauli measurements. Here, this is, for instance, a joint measurement of the operator ZZ on 2 neighboring qubits. So we measure ZZ on qubit 2, qubit 3. And the measurement outcome will be stored on bit 2. So this is storing the measurement outcome on the classical memory. The next operation we authorize is unitary Clifford operation. So not only measurement, but unitary Clifford operations, like a CNOT gate or H gate. And we also authorize classical control and classical communication. This is sometimes not allowed. We don't want to limit our circuit, and we don't want to give a negative result for only a small class of circuits. So we give as many operations as we can. So we authorize classically controlled Pauli operations. An example is here. This X operation is applied when the outcome of bit 3, when the value stored in bit 3 plus bit 5 has an odd parity. So if the parity is 1, you apply X. If the parity is 0, you do nothing. This is what is a classically controlled Pauli operation.
I have another question here, Nicolas. Sorry to keep interrupting you. So
no, that's great.
Someone is writing, this might be a stupid question. I think there are no stupid questions. So here comes the question. Are these operations enough to give you universal quantum computation?
So no, it's not a stupid question, because they are not enough to have universality. But what we want to do with this circuit is only run quantum error correction with those LDPC codes. And to have universality, we will add, for instance, a T gate, and we will inject T state and do distillation. I'm not going to talk about that in this presentation. We have protocol to inject to get universality on top of logical operations. And here I'm simply going to talk about running circuit to perform error correction. This is already difficult enough.
Okay, thanks.
So they are not universal. It's basically Clifford, but augmented with some classical communication. And one thing I want to mention also is that you see that this operation depends on bit 3 and bit 5. So it has access to the whole classical memory. And we assume instantaneous access. We don't limit the access to the classical memory. And the last thing we can do is taking the parity of some bits. So at the end of this circuit, we return the parity of 5 outcomes, 5 bits. And
okay, Nicolas,
yes.
I'm very sorry. I have another question here, but I think it's good to keep them going maybe when during the talk.
Yeah.
You said you were happy with the discussion throughout the talk. So here someone is asking, how fast does the classical communication have to be in order to, you know, what do they say, in order to keep the potential quantum speedups in an error-corrected computer?
Yeah, so it depends on the speed of your gates, your quantum gates on your qubits. But here we want to prove a negative result. So I'm going to assume instantaneous operations. And even with instantaneous classical communication, we will see that we still have big obstacles. So it still seems unlikely that it works. So it's not the bottleneck.
Okay, thanks.
And this circuit, for instance, what does this circuit do? It's measuring the parity of qubit 1 and qubit 7. So it's building something that is a cat state on the qubit 2 to 6. And at the end, it's returning the outcome of the measurement of XX on first qubit and last qubit. So we can do a non-local measurement using all this operation and measure the parity of 2 qubits at the end of a line of qubits. And now, here is the issue, is that if we consider a family of quantum LDPC codes with some form of expansion, which is a natural assumption for LDPC code, and if those codes encode our block of qubit into n qubits, but if we implement them with local gates in 2D, with square root of capital N times square root of capital N qubits in total, so including ancilla qubits, we have this number, this grid of physical qubits, then we have a lower bound on the depth. And the depth of the circuit is at least proportional with the block length, the length of the code, divided by the square root of the total number of qubits. And now, what does that mean? If we specialize this bound to 2 cases, the first case will be when can we have a constant depth? So we can have constant depth only if this bound is 0, is O of 1, sorry, is linear, is constant. And this happens when the total number of physical qubits of the grid is n squared. And that means we need n squared ancilla qubits. We need many ancilla qubits if we want constant depth. When for surface code, we can have depth 6 with a linear number of ancilla qubits. So there is a big extra cost here in terms of number of ancilla qubits. And the second regime we can consider is when can we preserve a constant overhead? So with LDPC code, we encode k qubits into n qubits, and k and n are proportional. The number of logical qubits is proportional with n, and we would like to keep that. To keep that, we can use only a linear number of ancilla qubits. So that means that capital N, the total number of qubits, will be proportional with n. And if this is proportional, the depth is at least square root of n. So instead of depth 6, we have a depth that grows with the code size. And it's an issue. These two bounds are tight. We have some circuits that reach this bound. And I'm gonna discuss one example of such a circuit. and we simulated this one that give us the constant overhead that we want for LDPC codes, and we'll see the performance later. Okay, so first I'm going to give you an example of a circuit that's saturating our band. So we have a class of circuits that works for all CSS code and that will achieve a constant depth. Just to show you what it costs to achieve constant depth syndrome extraction circuit with LDPC codes. So the goal of the syndrome extraction circuit is to implement a circuit that looks like that. This is the same circuit as an X plaquette. And this is what we need to implement a check with degree 4, a check that does the parity of 4 qubits for X measurements. Okay. And how do we do that? We prepare a plus state on an ancilla qubit that we're going to place on our check. And then we are going to implement our 4 CNOT along the edges of this check. And at the end of this CNOT, we measure the check. And we get the outcome of our check. We get our parity that we can use to run error correction, to correct errors. Now we want to do that in 2D. But before doing that in 2D, I'm going to give you an example. With a full code, not only with a single check. Okay, so with a full code, we proposed a circuit that is based on a coloration of this graph. So this graph with the checks, it's called the Tanner graph, and we can take a coloration of the edges in such a way that 2 edges with the same color do not share a node. This is what a coloration means in graph theory. So first we build an edge coloration, and then we will prepare an ancilla qubit, each check in the plus state. So we add an ancilla qubit for each check. Then we select each color. For instance, I select red, and along each red edge, I can apply a CNOT from the check to a data qubit on top. Okay, so we have 7 data qubits, and we can apply these 3 CNOTs simultaneously because they don't overlap, they don't share a qubit. So we can implement these gates simultaneously in parallel. Then we do the same thing for the green edges, 3 CNOTs on green edges, CNOTs on blue edges, and each time you see that they don't overlap. That's the goal of the coloration. And then we do a last round of CNOTs, and we measure our ancilla qubits. By doing that, we can implement all the checks simultaneously in 6 steps, in depth 6. And the depth is given by the degree of the graph. So it's 2 to prepare and measure the ancilla plus degree 4. So in general, for a sparse graph, we can implement the syndrome extraction in constant depths. We can measure all the checks simultaneously in constant depths. The issue is that here I'm assuming fully connected qubits. I'm assuming that this check can talk to any of the qubits. What's happening when we don't, if we apply only 2D local gates? And what I'm going to explain is how to implement those CNOTs. So first, so how can we implement those 3 CNOTs simultaneously on a 2D grid of qubits with only local gates, only gates acting on qubits at distance 1. So this is a grid of qubits. Each node is a qubit. Is a physical qubit. And you see that we need many physical qubits already. And we are going to start by embedding this code inside our grid. So the top qubit will correspond to the data qubit of the code. I give some space between them. I need some space. And the bottom qubit will be used to encode the checks. My 3 checks will correspond to the first 3 bottom qubits with some space between 2 qubits. Now we want to implement a CNOT from the bottom to the top, connecting some bottom checks to some top qubits. And the connections we want is connecting the first check to this qubit on top. I'm going to put the index of the check below. So I want to connect this qubit to the check 1, this qubit to check 2, and the first data qubit to check 3. To do that, we are going to build a set of paths connecting the top and the bottom. So we do that with a sorting network. So first I'm going to complete the indices of the remaining qubits. I'm going to put all the other numbers in increasing order. It doesn't matter in which order I put them. But the only thing I care about is 1, 2, 3. And we're going to use the odd-even sorting network. The goal of this network is to connect 1, move 1 in front of 1, 2 in front of 2, and 3 in front of 3. And we do that by sorting the first odd pairs, then even pairs, and odd pairs again, and so on. So here, when we sort that, we will swap 1 and 5 that are not in the right order. They are not sorted. So at the first round, we will swap 1 and 5 and 6 and 2. If I do that, I get 1 and 5 in the right order, 6 and 2 in the right order. And then I do the same thing on the other arrows. And if I keep doing that, I end up with, in the bottom, I end up with all my numbers in the right order. They are sorted. Now that I have that, I'm going to build path following those numbers, following those indices. And this path will connect the bottom check to the top qubits, to the qubits I want to connect to. So now the goal is to implement a CNOT gate from the bottom check to the corresponding data qubit on top. And to do that, so we know how to implement long-range CNOT gates using local gates, but the main issue is that they are crossing those gates. So I don't want to implement the first one and wait to implement the second one. I need to implement them simultaneously to preserve a constant depth. And to do that, we're going to build a small gadget that will allow us to cross path, to cross long-range CNOT gates. And this gadget is made with Bell states. So I'm going to explain here how we build these crossings. And they are built by preparing a Bell state. So we prepare a pair of Bell states, and then we swap them. We swap 2 of the qubits of the pairs, and we obtain a crossing Bell states. We obtain a crossing pair of Bell states. And these crossing pairs can be used to implement a long-range gate, but they can be used only once. Once you use them, they are destroyed. So it's a kind of virtual connection between 2 qubits that is made with entanglement, and once you use it, you need to rebuild it. So before we implement this long-range gate, we first build those Bell states, those crossing Bell states at each crossing point, and then we can use them to implement the CNOT gates from the bottom to the top, and to implement the 3 CNOT gates, long-range CNOT, simultaneously. That allows us to do the implementation of the syndrome extraction circuit in constant depth. We do exactly the same as the color-based circuit. So for each color, we are going to implement all these CNOT gates. The issue is that we need a grid of about n by n physical qubits. So we need many physical qubits, but we have a constant depth. And based on our bound, we cannot do better than that. This is tight. Okay, so now I'm going to move to the numerical results. So we have lower bound on the depth.
Sorry,
and we have
quick question for you.
Yes.
On your previous slide, this Bell gadget, could you not use it to do more than just neighboring swaps and straight up have your number 1 go to the right position and your number 2 go to the right position if you make these longer range Bell type gadgety swaps?
Yeah, we could do that. In some sense, it's what we do with the long range CNOT. So part of moving the Bell state is done inside the long range CNOT. But that's true. That's one other way to see it. You could.
But if you have your gadgets arranged like that, then you don't need any kind of depth, right? You can just have everything be sorted in one shot.
Yeah, everything is sorted in one shot.
Oh,
so
okay.
yeah. So maybe what was not clear is that what I was doing before sorting those numbers is a classical subroutine. So we sort the number just to build the path, but this is purely classical. Once we have the path, we use a quantum circuit that is doing the long range CNOT in 2 steps. First, you build those crossings, and then you implement the long-range CNOT in O of 1 in depth, in constant depth. But the time required for the classical preprocessing is negligible.
Okay, thanks.
Thank you. Okay, now what do we get numerically? So we have a lower bound on the depth, and we have circuits circuits that are optimal up to a constant in terms of depth. So they are as fast as possible. And with these circuits, we simulated with circuit level noise the performance of a family of LDPC codes. So this family encodes each qubit into 25 qubits. So instead of 1,000 like the surface code, it's only 25 physical qubits per logical qubit. And we simulated this circuit with two models. First, we assume the color-based circuit with fully connected qubits. This is on the right side here. And second, we assume only local gates in 2D and a syndrome extraction circuit, which is not constant depth, but square root of n depth. So of course, because the syndrome extraction circuit is longer, there is more noise. All the gates are noisy. And because of that, the performance is degraded. So instead, if here, the horizontal axis is the physical error rate. So the threshold, the performance becomes very good if we are below 10 to the minus 3 with fully connected qubits. But for the same codes, if we change the syndrome extraction circuit, we achieve roughly the same performance with physical qubit with an error rate of 10 to the minus 6. So we lose 3 orders of magnitude in terms of physical error rate. We need qubits that are 1,000 times better. This is a big gap, and this is the cost of having a 2D local gates only and having a 2D local circuit. So for this family, it's very expensive, and it seems challenging to build this family of codes with such a low physical error rate. So this is the conclusion of the numerical result, and I'm going to quickly discuss the circuit bound. So how do we prove this lower bound on the depth? This part is a little technical, but then I'm going to come back to something more graphical. So our lower bound is based on this result, which is if we consider a Clifford circuit that measures commuting Pauli operators, and we take a subset of qubit L. So L is the left side, and R is the other set of qubits, the other subset of qubits, the complementary. Then we have a lower bound on the depth that depend on L, and this lower bound depend on the number of cuts, which is the number of operators of Pauli operators Si that you measure and that cross the cut. So you count the number of operators with support on both sides of the partition. And the second thing you count is the number of gates that are crossing the partition. So DL is the boundary of L, is the number of gates acting on one qubit on one side, another qubit in the other side. So the number of CNOT gate crossing. And we have a lower bound that depends on that. If we specialize this lower bound to a square grid or a cubic grid, and we find the right subset L, then we obtain our square root of n lower bound on the depth. So all the results of this paper all the bounds of this paper are derived from this general bound on the depth. And what is the intuition for that? So the basic idea is to look at the correlations between left and right. We have this partition, and we are going to prove two results. The first is that the number of bits of correlations is upper bounded. And it's upper bounded by something that depends on the size, the number of gates crossing the partition times the depth. I'm going to give you an intuition why later. And we have also a lower bound on the number of bits of correlations. Combining these two upper bound and lower bound, we get exactly our result. We get that the depth is lower bounded by the number of bits of correlation times divided by this term, and the number of bits of correlation is lower bounded by that. So altogether, we obtain a lower bound on the depth. And the main difficulty of this proof was to find the right notion of correlations. I'm going to keep it vague in this presentation, but the right notion of correlation we ended with is some notion of condition mutual information between two subsets of outcomes, between what we observe on the left side and what we observe on the right side. And it's a bit technical to arrive to this point, but I'm going to try to give you an intuition for these two bounds. So first, the upper bound on the amount of correlations. The idea is that only gates that are crossing the partition can introduce correlations. If you have a gate that is acting on 2 qubits of the left side, they cannot introduce correlation between left and right. So we just have to count them. And at each round of the circuit, we have at most DL gates crossing the partition. This is the definition of this number DL. So it's the number of gates crossing the partition in one time step. And we need to multiply by the number of time steps to have the total number of gates crossing the partition inside the circuit. And by doing that, we get number of gates in one time step times number of time steps. This is the total number of gates crossing the partition, and there is a constant here. So this is our upper bound on the number of bits of correlation. And the lower bound is a little more technical. So to obtain the lower bound, we look at the correlation between the outcome observed on the left side and on the right side. And we look at these Pauli operators that we want to measure and that are supported on both sides of the partition, like SI here. It has 1 qubit on the left side and 2 qubits on the right side. If we want to measure something like that, we're gonna consider a circuit where we measure it twice. Why do we measure it twice? It's because if we measure it twice, the second outcome is the same as the first outcome. We get the same result. Quantum mechanics tells us that. So after projecting onto one of the eigenspace, we get the same outcome again. And now the outcome will depend on an entire circuit that will extract, that will use many ancilla qubits. And the outcome is going to be the parity of some ancilla qubits. Some of them are on the left side, some of them are on the right side. So I'm going to denote alpha I, the outcome on the left side, and beta I, the outcome on the right side. So we take a parity of some measurement outcomes that are implemented in the circuit, and that give us the measurement outcome of SI. And we do it twice. So the first time we get this measurement outcome, the second time we get other measurement outcome for the measurement of this inside the circuit, but the parity is preserved. So the outcome of SI is the same in both cases. That means that the sum of the alpha I plus the sum of the beta I equals to this second sum. And if we move all the alpha I on the left side and all the beta I on the right side, and everything I do here is modulo 2, then we get that the sum of the outcome that we observe on the left side and the sum of the outcome, the parity of the outcome on the right side are the same. We have parity, the same parity on the left side and the right side, and this is exactly 1 bit of correlation. So each time we have a circuit acting on both sides, an operator acting on both sides, and we want to measure it, we get 1 bit of correlation. This is this lower bound on the amount of correlation. And combining lower bound and upper bound, we get the lower bound on the depth. Okay, I'm done with the most technical part. Now I'm going to get back to long-range connections. So there was a question about that. I'm going to explain what are our layers. But before that, what is the most naive design that you can do for a quantum coder, for LDPC codes? And the most naive design you can do is you put your qubits on a circle and you connect everything when you need to connect them. It's what it looks like if you have 100 100 qubits, 100 vertices with degree 8. So each qubit is connected to 7 other qubits, and it looks like that. It looks a bit messy, and that's the issue. Is that if you want to implement that, we are worried that all these crossing wires, all these crossing gates, will introduce correlated errors. Crosstalk will lead to correlated errors, may lead to correlated errors, and it's going to degrade the performance of the code. The code is not going to perform well because of that. So we want to avoid those crossing gates. We want only a small number of crossing gates, and we also want a short depth, because we saw with the previous example that large depths leads to poor performance, too much noise during the syndrome extraction. But can we do that? Can we have something with no crossing and short depths? And this is what we get by looking at graph drawing. So we use results from the theory of graph drawing. And what we do is that we will decompose our Tanner graph into layers, into planar layers. For instance, here, I can move the qubit wherever I want. So I move the check qubit on top, and I can implement the first check and the second check in a planar way, right? There is no crossing gate here. And then this is one of the layers, and the second layer is the second check, which is also planar by itself. So here I have 2 layers, and I have a 2 planar layout for Hamming code, for this code. And more generally, if we start with a CSS code, and if the degree of the Tanner graph, the degree of the graph that defines the code is delta, so we assume it's a small number, then we get delta over 2 planar layers of gates, and we get a depth which is 2 delta plus 2. And in the case of hypergraph product codes, we can even improve the depth further. We can remove the factor 2. So it looks like that. Instead of having qubits with many crossing like we see in this picture, we'll have a square grid of qubits with 4 layers of gates, and inside each layer we have no crossing. So this is the one we simulated correspond to these 4 layers. And what are the results? What are the simulation results? So we assume that we have long-range gate. It's a significant assumption. It's challenging to build, but if we do have that, we obtain a threshold of about 0.3%. The surface code threshold is higher. I said 1%, it's actually about 0.7% for the same noise model. So the threshold is about twice lower, but the number of physical qubits is very small. The number of physical qubits per logical qubit, including all ancilla qubits, is 49. So we have about 50 physical qubit per logical qubit, counting all the qubits. It's an overhead of a factor of 50 instead of a factor of 1000. And if we look at the number of physical qubits we need to achieve a given logical error rate, so if depending on the application you want to run, you may want to have a logical error rate of 10 to the minus 9, minus 12, minus 15. So minus 15 is for chemistry, for instance. So if you want to run a chemistry simulation that requires a logical error rate of 10 to the minus 15, you will use about 15 times fewer qubits with this family of codes than with surface codes. So you have a significant saving in terms of number of qubits using LDPC codes, using quantum LDPC codes. Okay, now I'm going to move to my conclusion. So the first, our main results are circuit bounds for 2D local circuits, and I think it could have application beyond syndrome extraction circuit. Measuring Pauli operators is something we do everywhere. And we designed and we simulated different classes of 2D syndrome extraction circuit so that we have a clear simulation result with realistic noise models. And we observe that quantum LDPC code can outperform surface code, even with accurate simulations. and with a 2D layout, if we have long-range connection, we can outperform surface code. So it's very encouraging. And in the future, I'm hoping that we can improve further quantum LDPC code. One of the first things we can do is use a better family of codes. As I was telling you at the beginning, there was some recent breakthrough constructing LDPC code with larger minimum distance, capable of correcting more errors. If we replace the code we simulated by these codes, we should be able to get not a factor of 15, but maybe a larger gap with the surface code. So we can keep improving the performance of this code, improving the circuit, improving the decoder. There is a lot of potential for improving these codes and to increasing this 15x gap. And the second thing we need to do is fault-tolerant logical operations. So there was a question about universality. Here, we discussed only quantum error correction. So we need ways to implement logical operation on top of that. There is different proposal. I think it's a very exciting direction. And there is different proposal by Joachim O'Connor or by Krishna and Poulin, or more recently by Cohen, Kim, Bartlett, and Brown, or Breckman and Burton. And you have different proposals to implement logical gates for LDPC codes, for quantum LDPC codes. And on the experimental side, I see two challenges. The first one is, can we design reliable long-range connections? We would like to have long-range connections that are capable of connecting 2 qubits at the two endpoints of a chip. And we want the noise rate to be low enough, to be proportional, same order as the noise rate of other gates on the chip. It's a challenge in itself, even building one connection, but we need many of them. We need many long-range connections. And then we need layers of long-range connection that are insulated from each other, so that we have little crosstalk between the layers. We have time. It's not the codes we are going to build right now. We need thousands of qubits to build this kind of error correction scheme. But it gives us a few years to explore the potential of this code and the experimental challenge. Thank you.
Thanks so much, Nicolas, for a really nice and clear talk on your work on LDPC codes. Let's open up. I know that a lot of the students have lectures in 3.5 minutes, but for those of you who are still on the call, if you have any questions you'd like to ask, now is your chance. See that Hugo already has raised his hand, so I assume that you have a question, Hugo.
Yeah, I can start off with another question. Yeah, thanks for this talk. This was really great. I was wondering if you could comment on the scaling that occurs. So I think throughout this you assumed this 0.1% error on your physical qubit, right? How does this scale if you have either worse qubits or better qubits?
So we don't assume a fixed error rate. We simulated the performance for different noise rate.
Yeah.
Here we simulated between 10 to the minus 3 and 10 to the minus 4. And this table is based on an assumption is that we need to be far enough below the threshold. Okay. If we are too close to the threshold, it's going to take very large codes to get a good performance. It's possible, yeah, but ideally we want to be about 1 order of magnitude below threshold. So for the surface code, we often consider the regime of 10 to the minus 3, which is about 1/10 of the threshold. And here we consider a regime of 10 to the minus 4 to build this table. So we need better qubits than with the surface code to implement these larger codes.
Okay, yeah, I see. Yeah. Thanks.
I have a question written here. Let's see if I understand it correctly. So I think the question is about these grids of connected qubits. So basically they say you have a grid of connected qubits and you assume a certain physical error rate, what happens if 1 or say 5 of these qubits are much worse? Will the whole thing fail, or is it robust so that the average physical rate, I guess physical error rate, should be below this value?
Yeah, I mean, there is some robustness. It doesn't break down immediately, but if a few qubits are bad, it can degrade the performance. So if we use the minimum distance to measure the performance of surface codes, for instance. So it's the size of the surface code grid, right? Here it's a 25 by 25 grid. It's a distance 25 code. If one of the qubit is very bad, it's maybe going to behave like a 24 by 24 grid. So the performance is degraded a little, but you see that if this happens, you can just increase the size of the grid and it will still perform well. So it's pretty robust.
Okay, cool. Thanks. Let's see if we have any other questions. I think maybe I will ask just a general question then. So you mentioned a bit of like future work and stuff like this, but what do you see as the kind of most exciting venue for things in the next few years? What would be the kind of main result people are working towards at the moment?
You mean in quantum error correction in general?
Yeah, or in LDPC codes. It's asked in a broad way, so you have the freedom to interpret as you like.
Yeah, so on the general side of quantum error correction, I think quantum error correction is the next breakthrough. We have a quantum superiority experiment at Google, which is, and even in China, which is pretty amazing. But now we need logical qubits. We need error-corrected qubits to have large-scale applications. And right now, as far as I understand, there is not a single experiment that provides a logical qubit that is fully satisfying, that does logical operation better than all the physical operations. So this is, to me, this is the next breakthrough, to have a logical qubit experimentally that is better than the physical qubit it's built on. And it's non-trivial. It's a lot of experimental work in particular.
Yeah.
And on the side of LDPC codes are longer term. It's not the first thing we are going to implement. But I like the question of improving quantum LDPC code, building new classes of quantum LDPC code. There was many recent breakthrough with this kind of question, and building logical gates. To me, it's beautiful mathematical questions, and it can be very useful.
Okay, Nicolas, thanks a lot again for joining us. If you want to stay on the call for a few more minutes, we can have a bit of a chat afterwards. If you have to go, no worries. But for everyone else, we'll see you next week when Matthew Pusey will be talking about foundational questions in quantum mechanics.